Hey, all right. We're going to start section 5.4, and this will wrap up our discussion on polynomials. Um, in the subsequent sections, we will be moving into rational functions. So in class on Wednesday, we started discussing what complex numbers are. In this video, we're going to build on that discussion and talk about how complex numbers show up in polynomials. So we're going to start with first reviewing a factor theorem. In section 5.3, we explored techniques for factoring roots out of polynomials. And it turns out that for any polynomial, let's say f of x is a product of linear terms and quadratic terms. So this holds when the polynomial has real coefficients, and essentially says that the polynomial can be broken down in a unique way into just linear terms and quadratic terms. So a linear term is something that looks like x minus a, and a quadratic term looks like x squared minus ax, or plus ax plus b. So if we have a polynomial, say f of x equals x to the fourth minus 1, then we can break this down into linear and quadratic terms using the difference of squares trick. We know that it can be factored like this to get x squared plus 1 times x squared minus 1. And pause the video and FOIL that out just to make sure that that is correct. Now for that second term on the right, we can actually find roots for that. We know that x squared minus 1 can factor down into x minus 1, x plus 1, and we still have this x squared plus 1. So this is our factor theorem at work. We've reduced down to having two linear terms and still this one quadratic term hanging about. If we introduce complex numbers, we can actually factor x squared minus 1 down to linear terms. So if we notice that x squared plus 1, we can find the zeros of it by just setting it equal to 0. So we have x squared equals negative 1. And that tells us that we get that x is plus or minus the square root of negative 1, which is plus or minus I. And so that allows us to express our polynomial in full linear terms. F of x equals x minus 1, x plus 1, x minus I, x plus I. And these zeros, the plus and minus I, still work the same way as all the zeros that we've seen before. If we evaluate f at I, we're just going to plug I into our equation, I to the fourth plus 1. Sorry, I to the fourth minus 1. And I to the fourth is I squared times I squared minus 1. So that's -1, -1, -1, which equals 0. And so there we have it. So pretty much the process for finding complex zeros, as it goes with this class, is going to be breaking a polynomial down into its quadratic and linear terms. Our goal is to break and then we actually apply the quadratic formula. So we apply the quadratic formula to find complex roots. Of course, that's not what we just did above. But if we had a polynomial that looked like f of x equals x squared plus plus 2x plus 20, then we can find complex roots just through the quadratic formula. The quadratic formula implies that x equals -b plus or minus our square root of 4 minus 4ac, so that's 80 all over 2. So then x equals -2 plus or minus the square root of -76 over 2. And we just pull that negative out in front as an I. And that then allows us to see that our polynomial f of x factors into linear terms as x plus 2 plus I root 76 over 2 times x plus 2 minus I root 76 over 2. And that's really all there is to it. It's always just going to be using the quadratic formula or a different factoring trick to find these complex roots. And this always works where it factors down into linear and quadratic terms when we have real coefficients for a polynomial, meaning our polynomial looks like, when it looks like a sub n, x to the n, plus so on, all those a's in front are just real numbers like 2, 1/2, pi, square root of 5. We don't have any complex numbers out in front. For this class, that's usually assumed to be enough. You have to be in a pretty weird situation to be getting complex numbers in front of the coefficients on your polynomials. I think it does come up in quantum mechanics and maybe some advanced electrical engineering if you're studying impedance. But for this class, we're just going to stick with the real coefficients. All right, we'll break here as just an intro for this video, but there will be more to follow.